on to Lesson 4 of the Healthcare Packaging Sustainability course. As we know, packaging plays a crucial role in maintaining the sterility and safety of medical devices and products. However, the environmental impact of packaging has often been ignored. For many years, healthcare packaging has been exempted from sustainable packaging legislation to protect patient safety, and rightfully so. But as the world shifts towards a more sustainable practice, the healthcare packaging industry is now being looped in. In all industries, designing for sustainability involves integrating the principles of the waste hierarchy, reduce, reuse, and recycle, into every stage of packaging development. This approach not only minimizes environmental impact, but also aligns with emerging regulations and industry standards, such as ISO 11607 and EU PPWR, that we learned about in Lesson 2. So let's explore how these principles of sustainable design can be applied effectively in healthcare packaging. Sustainable packaging is defined by Smithers as any form of packaging where a conscious, significant effort has been made to reduce the environmental impact of the package. This includes the ability of the packaging to increase shelf life, reduce spoilage, damage, breakage, and waste of the packaged product. According to the Sustainable Packaging Coalition, 70% of the overall impact of a product is determined in the design phase. When it comes to packaging, adopting a reduce, reuse, recycle approach is crucial for sustainability. So let's define what components of the waste hierarchy are. First, we have reduce. This focuses on minimizing waste generation and environmental impact from the start by reducing material usage and avoiding unnecessary resources. Next, we have reuse. This involves extending the shelf life of products and packaging and materials through repeated use, reducing the need for new resources. Re-sterilizing medical devices and metal trays are a prime example of reusable packaging in healthcare. Devices that can be safely cleaned, sterilized, and reused help extend the product's life cycle and reduce the need for new materials. This practice not only supports sustainability, but also provides cost savings for healthcare providers. In addition to reusing the devices, the trays can be sterilized and reused multiple times. These devices and metal trays are traditionally re-sterilized in an autoclave within a hospital. Once sterilized, the devices are packaged with polypropylene glue wrap and sent out for reuse. By designing packaging with reuse in mind, healthcare facilities can significantly reduce their waste generation and material consumption. Lastly, there is recycle. Recycling is the process of collecting and processing materials that would otherwise be thrown away as waste and remanufacturing them into new products. Since the majority of healthcare packaging is single-use, we are going to talk about the design for recyclability within the healthcare packaging landscape. According to the Healthcare Plastics Recycling Council, in 2020, over 32 billion pounds of healthcare plastics were produced globally, and that is expected to grow to 48 billion by 2025. Most of this material is being disposed of in landfills or incinerated. The best thing we can do as healthcare packaging suppliers and producers is to design our packaging to be recycled. Once the healthcare industry builds infrastructure to collect, sort, and recycle, we will have products and packaging that are ready for recycling. There are plenty of tools when designing for recyclability, such as the Association of Plastic Recyclers Design Guide, ReciClass, SPC, and more. However, different design guidance for healthcare packaging is essential because there are unique requirements that differ significantly from regular consumer packaging. Healthcare packaging must prioritize sterility, patient safety, and compliance with stringent regulatory standards, which often involves using specialized materials that may not be easily recyclable. Additionally, healthcare packaging must withstand sterilization, protect sensitive medical devices, and maintain product integrity throughout its shelf life. Therefore, dedicated resources such as the Healthcare Plastics Recycling Council Design Guidance is crucial to navigate these complexities of healthcare space. It ensures that healthcare packaging meets both functional and recyclability guidelines, helping the industry circulate material while maintaining the highest levels of safety. HPRC's design guidance categorizes packaging selections into healthcare preferred, healthcare less preferred, and healthcare not preferred. Healthcare preferred is preferential materials or design options that optimize recyclability. Healthcare less preferred is a less preferred material or design option that does not optimize recyclability, yet has been proven to consistently meet product and safety requirements. Consideration should be taken into transition to a healthcare preferred option when a product safety can be matched or exceeded. Lastly, healthcare not preferred is material or design options that do not optimize recyclability and should be avoided whenever possible. There is guidance on rigid thermoform trays, porous lidding, non-porous lidding, powder bags and vent bags, porous and non-porous pouches, films, barrier materials, and labels. The main section of the design guidance includes material selection. We must optimize materials that are commonly accepted by healthcare and recycling facilities, such as certain types of PET, HDPE, and polypropylene, while avoiding materials that complicate recycling processes, such as multi-layer films. Design for disassembly. It is best to create packaging that can be easily disassembled into its components and materials, facilitating for more efficient recycling and reducing of contamination. Minimizing contaminants. Avoid using labels, inks, adhesives, and other components that can interfere with the recycling process or degrade the quality of the recycled material. Standardization. It is encouraged to use a standardized material and design features that simplify the recycling process and enhance the recyclability of healthcare plastics across the industry. Lastly, we have testing and validation. Include recyclability testing as part of the packaging development process to ensure that materials meet design for recycling criteria without compromising the product safety. Next, we are going to talk about reduce in terms of minimizing material and carbon footprint. First, reducing material by volume. One of the most effective ways to reduce environmental impact is by minimizing the amount of material used in packaging. This can be achieved through downgauging, which involves reducing the thickness of packaging materials without compromising their protective qualities. By optimizing packaging design to use less material, manufacturers can significantly reduce the volume of packaging waste and carbon footprint of the package. Next, we have reducing fossil fuel-derived plastics. Reducing reliance on fossil fuel-derived plastics is another critical aspect of sustainable packaging. Advanced recycled materials allow for the creation of high-quality plastics from waste that would otherwise be incinerated or landfilled. As we know from Lesson 2, these materials maintain the same performance characteristics as virgin fossil fuel-derived plastics, while reducing the need for new resources. Bio-based materials are emerging on the market in the food and consumer space, but also can be evaluated for certain healthcare applications. Bio-based materials can function similarly to regular plastics because they often have comparable chemical structures and properties. For example, bio-based polyethylene or bio-based PET are chemically identical to conventional polyethylene or PET, allowing these materials to offer the same durability, flexibility, and barrier properties. These materials can be processed using the same manufacturing techniques and are suitable for similar applications. Therefore, materials derived from advanced recycling technologies or bio-based sources can not only reduce our reliance on fossil fuels, but also provide a lower carbon footprint option for our packaging. Lastly, we have reducing carbon footprint through LCA. LCA is life cycle assessment. This is a powerful tool for measuring carbon footprint of packaging throughout its entire life cycle, from raw material extraction to disposal. By conducting LCAs, manufacturers can identify areas where carbon emissions can be reduced, such as through material selection, energy-efficient manufacturing processes, and optimized transportation logistics. In this example, we are evaluating a 35 ml PETG tray with an LLDPE header bag with Tyvek. Just by down-gauging the material by 5 or 10 ml, we can decrease the carbon footprint by 10.5% for 5 ml or nearly 21% for 10 ml reduction. Simple design optimizations can decrease the carbon footprint of this packaging system by another 7% to reach a total of 27% reduction in overall carbon footprint. Simple assessments such as this can show what is truly possible when reducing material usage and optimizing design. In this next example, we are evaluating the use of bio-based PET or recycled content for a secondary healthcare package. As we can see from the results, incorporating 30% bio-based PET results in an 8.5% reduction in overall fossil fuel usage, and incorporating 30% of post-consumer recycled PET results in a 23% reduction in fossil fuel usage. Again, this is a great tool to research the best options for minimizing our reliance on fossil fuels and decreasing our overall impact environmentally. In addition to reducing the volume and carbon footprint of packaging, it is essential to eliminate materials of concern, such as PFAS, that may have negative environmental or health impacts. Eliminating PFAS from medical device packaging is crucial because these substances are linked to serious health risks, persist in the environment for centuries, and face increasing regulatory restrictions. Removing materials of concern helps protect patient health, reduces environmental contamination, ensures compliance with regulations, and builds consumer trust in safer, more responsible products. In this scenario, it is best to collaborate with environmental health and safety, product stewardship, quality assurance, and regulatory experts on how best to handle eliminating materials of concern. Lastly, closed-loop recycling is the ideal scenario where packaging materials are collected, recycled, and used to create new packaging. As you can see with the schematic, this system ensures that materials are kept within the production cycle, reducing the need for virgin resources and minimizing waste. By incorporating closed-loop recycling practices, healthcare packaging can become a part of a sustainable cycle that continuously regenerates its own resources. Closed-loop recycling options are great for packaging used in pharmaceutical or diagnostic settings, such as work-in-process trays or other packaging formats that stay within the manufacturing environment. To close, designing for sustainability in healthcare packaging is not just about meeting regulatory requirements. It's about taking a proactive approach to reduce environmental impact while maintaining the highest standards of safety and efficacy. By applying these principles of the waste hierarchy, reduce, reuse, and recycle, manufacturers can create packaging that supports a circular economy, minimizes waste, and reduces reliance on finite resources. As the healthcare industry continues to evolve, sustainable packaging will play a crucial role in protecting both patient health and the environment.